So, in this lecture, I would try to find out the Gibbs phase rule and etc. for a somewhat larger system and introduce you to the complications that are induced by fluids. And it's not very easy, but I will start a little bit with the fluids first, and then we go into the assemblage. I don't know whether I will be able to go further. I want to do this slowly so that you can get the full hang of it before we go into further complications. Right. We all know this equation, this reaction. Muscovite, you must have written it somewhere or the other. Now, this is an equation which you must be familiar with. This term might be unfamiliar. It's not a mineral, it's called aluminosilicates, AS. So it could be sillimanite, andalusite, or kyanite. And so it's time possibly to start writing equations a little bit, reactions a little bit. And say, for example, the formula for muscovite is the idealized formula is KAl2 Al Si3 O10 OH twice. Quartz is Si. SiO2. K-feldspar. This has several polymorphs. I don't know whether you know. Say, for example, the high temperature form is called sanidine, S-A-N-I-D-I-N-E. Then you have orthoclase, which you might be familiar with. Then you have microcline, M-I-C-R-O-C-L-I-N-E, and adularia, A-D-U-L-A-R-I-A. And this is some sort of a temperature variation. Sanidine, orthoclase, microcline, adularia. Progressively lower temperature polymorphs, broadly speaking. K-feldspar, and this is formula is KAlSi3O8. Aluminosilicate, Al2SiO5. You can see here I'm taking very generalized formulas. Very simple formulas, not going into any sort of complication. And the fluid is H2O. Fluid is H2O. These are phases and these are formulas, meaning phase components. All of them are taken to be pure. All of them are taken to be pure. And that is why I have written only one end member component. I have not put in any variations in this. But you know, K-feldspar is a solid solution between NaAlSi3O8 and albite, which is NaAlSi3O8. But I have not considered that. We will come to that later on. Quartz, we have taken pure. Muscovite, there is an N-member composition of muscovite, classical composition of muscovite. I have not added celadonite component to it. So you know, if you add celadonite component, your mica becomes sphengitic. So I have avoided all complications. Aluminosilicate, Al2SiO5, and fluid, we say, is pure H2O. Now the reaction, if you write, it is like this: KAl2, AlSi3, O10 OH whole twice, these are the reactants, plus SiO2 is equal to KAlSi3O8 plus Al2SiO5 plus H2O. This is the famous reaction by which muscovite, this is the low temperature side, this part is low temperature part, and this is the high temperature part. Now, if I draw a diagram, temperature, pressure, and this is how the reaction looks like, with muscovite and quartz to the left, low temperature, and K-feldspar aluminosilicate H2O. H2O, of course, you can't see, so K-feldspar aluminosilicate is the high temperature form. I will introduce you to a small term which you read in class 12. It is called the Clausius-Clapeyron equation. The formula is dP by dt is equal to del SR by del VR. This is the equation. dP by dt is equal to del SR by del VR. We will talk about this equation a little later. This is the entropy change of the reaction. That means entropy of the products minus the entropy of the reactants. This is delta VR. It's called the volume change of the reaction, which is volume of the product minus the volume of the reactants. This is delta is always product minus reactant. R subscript means a reaction. So you see here, if this is the nature of the curve, then if I draw a tangent at this point, and if I draw a tangent at this point, so you can see here, dP by dt tends to infinity. Whereas if I take it here, dP by dt tends to 0. It becomes flat like this. It's not 0, but tends to 0. This is not infinity, tends to infinity. This is dP, change in pressure as a function of temperature. Change in pressure as a function of temperature, you can see. Large pressure difference, small temperature, large value of P, very small value of T, so it's infinity. And this is just the reverse. Large value, small value of P and a large value of dT. It is the same as this is dP and this is dt. Right? Okay. So what we see here in this reaction, the slope of the reaction, that means the dP by dt of the reaction tends to 0 at low pressure temperature, and dP by dt tends to infinity at high pressure, high temperature. Now, if dP by dt tends to 0, that means delta VR should be very large, yes or no, compared to delta SR. Have you understood? dP by dt, if this is equal to 0 or tends to 0, that means the denominator, which is the delta VR, should be very big compared to del SR, or del SR should be close to 0. Normally, and in this part, dP by dP is very large. How can you have this large? If delta VR is small. Have you understood? So why this change of graph? Is because of a very simple reason. Because of this gentleman called H2O. At very high pressure, H2O, you know, is a fluid, is a highly compressible thing. So if you increase pressure, the volume of H2O, the molar volume of H2O decreases dramatically. But if your pressure is very low, then the delta VR is large. Do you understand? So in this type of a reaction normally, since delta VR is very large, because the highly compressible delta VR is very large at low pressure, so the reaction slopes are gentle. Whereas at higher pressure, delta VR is much large, the pressure is much large, and this dramatically decreases the delta VR of this place. That is why many of these reactions, or most of this reaction, have this type of a slope. The change in slope is because of the compressibility, fluid compressibility as a function of pressure. At high pressure, it has a small volume. At low pressure, it has a large volume, and hence the change of dP by dt. This is just for your information. Now, where am I keeping this? Here. I will draw this diagram again. Now, all these phases must provide quartz, K-feldspar aluminosilicate. These are all pure phases. Let us say the fluid. I think what I will do here, I will write fluid and then write H2O. Okay, so here, fluid is the phase. We will talk about it in greater detail later on. Fluid is and composed of H2O. Right? If we take the fluid also as pure H2O, then for a pure fluid, XH2O equal to 1. There is no doubt about it. So what we write here is 1. This value is XH2O equal to 1. But what happens? XH2O may not be 1. It can be less than 1. It cannot be more than 1. I will tell you a little. I will tell you. So pH2O, partial pressure of H2O, is equal to XH2O into P total. Total is the lithostatic pressure and pH2O is the partial pressure. At XH2O equal to 1, the partial pressure of H2O is the same as the overload pressure. Have you understood? If pH2O H2O is greater than P total, then you can imagine the pressure of the fluid is more than the pressure above it. So this will cause cracking of the overlying crust because nature does not tolerate this. So what happens is, if you have a fluid over pressure, then the rocks above it would crack to release the extra H2O. But there is no harm if pH2O, it has been reported, calculated from many terrains all over the world, especially high-grade terrains, where pH2O is less than P total. If that has to happen, then you can see here, XH2O will be less than 1. If pH2O is less than the P total, then XH2O necessarily should be less than 1. So what happens to this graph when XH2O decreases? This graph, you have to find out, but I will give you the clue. The graph, the reaction, the PT loci of the reaction, or the PT locus of the reaction, would shift to the left in a direction opposite to where this occurs, H2O occurs. So the fluid will move in a direction opposite to where H2O occurs. This is called from Le Chatelier's principle, which you studied in your school, or law of mass action, which you studied in your school. You please read it up. If you reduce XH2O value from the position of 1, the graph moves away from in a direction opposite to where fluid H2O occurs. So what happens is, this graph changes its position. So I am writing it, it's not correct of course. That's it. This is a truth. XH2O, when you decrease it, or you can say it, the stability of the low temperature mineral. So if you decrease H2O, then what is happening? The stability of muscovite plus quartz is getting more restricted to the lower temperature. Have you understood? This is a truth for all metamorphic reactions. That if you reduce XH2O, then the stability field of the low pressure, low temperature assemblage shrinks to lower pressure and low temperature. In other words, this assemblage, K-feldspar plus aluminosilicate, this assemblage shifts to lower temperature, or making K-feldspar plus aluminosilicate more stable at lower temperature and lower pressure. This is an important point that will come into our discussion. Now once again I make myself a little clear so that we understand everything. We have muscovite plus quartz is equal to K-feldspar per aluminosilicate. So you have the fluid composition as H2O, and you can reduce XH2O, then the reaction curve moves to the lower temperature, lower pressure side. That means muscovite plus quartz becomes less stable for low H2O, but extends its stability to a high temperature if the rock is hydrous. So this is wet rocks and these are dry rocks. Wet rocks and dry rocks. So as you wet the rock, the stability field of the low temperature form increases towards higher temperature. And if you dry the rocks, the opposite happens. This is a well-known fact. Now, the same thing you could do if you might be wondering, Acha, if you have a fluid and you're reducing XH2O, fine, the curve moves this way. But say, for example, when XH2O is 0.2, what is there? What else is there? Because for a phase, you should have summation sigma xi, or you should have sigma xi equal to 1. So if your XH2O is 0.2, where is 0.8? What is 0.8? This is a discussion that we will do later on. Thermodynamically, it is not necessary to have anything else. Anyway, for the moment, we will not consider this because, if I go into that mold, then I will losing connect with my earlier lectures. I have only told you this because it's a thing that should be remembered in your mind. Because we'll come back to this several lectures later, and then you will find why I was saying this. So, here in this, if I write it this way, then in wet rocks, it will change. Now, I will give you a escape route so that you're not tormented. You're not tormented. I will give you an escape route. I will do this with a red pen. Let's say you have a binary fluid. Have you understood? You have a binary fluid. The fluid is this and it is H2O, so that your original this thing Xi equal to 1, meaning XH2O fluid plus XCO2 fluid equal to 1. So that now you say, okay, I'm a little bit relaxed. There's nothing to relax. This is just because I want to help you out to understand it. So my fluid, when I say fluid, phase, then your sigma xi is equal to 1. That means XH2O plus XCO2 is equal to 1. Right? But remember, out of these two, only one is an independent variable. If you know XH2O, XCO2 is already fixed. Right? If you know XCO2, XH2 is fixed. So one variable is involved here. But if your fluid is pure H2O, like here, there is no XCO2. Right? No XCO2. That's for sure. Right? So now, we go into a domain which requires a bit of understanding. Now, I take this, I will first assume this graph, that means XH2O is equal to 1. Have you understood? That means for the moment I am ignoring this. I am ignoring this because XH2 is equal to 1. CO2 has no role to play. Right? So now, if these are the formulae, excluding CO2 again, what are my system components? What are my system components? You can see here, my system components are K2O, Al2O3, SiO2, H2O. It could be written in some other way, but it doesn't matter. K2O, Al2O3, SiO2, H2O. 4 component system, where all the phases are there. And so here C is equal to 4. 1, 2, 3, 4. You see, I can write all formulas in terms of K2O, Al2O3, SiO2 and H2O. All formulas. So here C is equal to 4. What is P? You can see 1, 2, 3, 4, 5. Oh, 1, 1, 2, 3, 4, 5. 5. So phase 1, 2, 3, 4, 5. P is equal to 5. So F is equal to C minus P plus 2, which takes it to 4 minus 5 plus 2 is equal to 1. So muscovite quartz, K feldspar aluminosilicate, we don't distinguish kyanite, sylvanite and halloysite. We assume it's a phase. Aluminosilicate is a phase. Whatever that phase is. We'll talk about that later. So K feldspar aluminosilicate fluid, all are phases. So you have 5 phases, 4 component system. So you have 1 valence. What does this mean? 1 is the valence. From other classes you must be knowing now, one variance means that one input, one variable is not quantified. One variable is not quantified. If you can do this, then the other variables can be quantified. Now I ask you, what are the other variables? What are the other variables? Is there any variable to do? Let's say, what are the variables? You can see here, pressure and temperature. These are the 2 variables of this line. Is there any other variable? Say, for example, XH2O. What is the variable? But the value is already quantified, isn't it? We have taken pure H2O. So the variable is already quantified. So that XH2O is not a variable. Not a variable. What are the other things? The other things are all pure phases. So all of their activities, phase component activities, are unity. Unity, all are pure phases. Also fluids. As we have taken it along curve 1. All are fluids. So, C equal to 4, P is equal to 5, F is equal to 1. Which means that if you assign a particular pressure value, one of the unknowns, if you assign, that means you write P is equal to 5 kilobars. P is equal to 5 kilobars. That means P is equal to 5 kilobars in equation. You know, number of variables minus number of equations is equal to, variance is equal to number of variables minus number of equations. That is what is variance. How many, it gives you how many variables are unquantified. So if you add P is equal to 5, then adding one equation yourself. So you're adding to the equation. So variable minus equation now becomes 0. That is no variance. That means if you take this value P at this curve XH2O, this is your T. So T is fixed. That is what Gibbs phase rule says for this curve. Muscovite plus aluminosilicate plus H2O. You say that I take a pressure value, so P is equal to something. You add an equation at the end, and therefore variable minus equation now becomes equal. So variance becomes 0. Of course variance becomes 0 because now you can directly find out temperature. Right? Similarly, you can go the other way. You can take the temperature and it intersects this curve here, and then you get the pressure value. I hope you have understood it. I hope you have understood it. Now comes the more difficult part, and that's the suspense. Now, have a look. If I take my fluid on the binary system, now what happens? In the binary system, my fluid. Now, instead of this, you also need CO2. Yes or no? Because the system component has to describe this composition. Unless you have CO2, you cannot write for CO2 because CO2 does not occur anywhere else. So now what you have done is, you have increased this one to 5. Right? Increased this thing to 5. But P, same. 1, 2, 3, 4, 5. 5. So 5 remains 5. So now we start 5 minus 5 plus 2. There you go, 2. What is this 2 now? Gibbs phase rule tells you that if you want to quantitatively characterize your equilibrium, then you need to give me 2 variables. 2 variables you need to give me external to the system, and I will give you the rest of it. Now, what are the variables? What are the variables? For muscovite, quartz, K-feldspar, aluminosilicate, no change. They are no solid solution. They are all pure phases. So the variables now are pressure, temperature, and now XH2O is a variable. You see that? Now your XH2O is a variable. Gibbs phase rule tells you your variance is 2. And your variables are pressure, temperature, XH2O. That means if you give either of these 3, either 2 of the 3, the other can be quantified. Either 2 of the 3 and the third one will be quantified. So out of the 3, there are only 3 variables possible here. Out of this 3, Gibbs phase rule says if you can quantify 2, any 2, I give you the third. The third can be computed. What is it like? Now we go back to this diagram. You see here. Look here. What is there? XH2O equal to 1 is off. It's out of the question now. But all values other than 1 and less than 1, all values are applicable. So so this is the pressure value. You have assigned P is equal to, so in the equation, number of variables minus number of, what is variance is equal to number of variables minus number of equations. So now I have added P is equal to something. So the variance was 2. Now when I add P is equal to 10, I reduce one equation because I've given you one equation. Now the variance becomes 1. Now if I tell, so that means if at this pressure, if you have this XH2O, this XH2O, this XH2O and this XH2O, they will give you different temperatures. Have you understood? So, you have to know which curve represents your equilibrium. That means you should know the XH2O value of your system. Right? That means if XH2O is equal to 0.2, then this is the temperature. If XH2O is 0.4, this is the, remember, this is the pressure, right? This is the pressure. So, if you have XH2O, then you get different temperature. Different temperatures. If you have different XH2O.